Advanced Algebra Data and Statistical Reasoning Standard 2.4 definitions. A z-score is the number of standard deviations a measure is from the mean of a data set. So z-score is how many standard deviations you are away from the mean. The z-score formula is given as follows. Okay, you got a lot of symbols there, so let's tell you what the symbols are. Z, of course, is z-score. X is just a measure within a population. So you have a bunch of people. We can use heights of Americans, let's say a 5'5" or 65 inches. That's a particular measure within a population. That's what X is, the measure you're interested in. This is Greek letter mu, and it stands for the population mean. Lowercase Greek letter sigma, population standard deviation. Okay, so we know z-score has to do with the two in tandem, standard deviation and mean, and this is the formula. So simple calculation, the mean of population is 50 with a standard deviation of 10. Find the z-score of the measure 35. Okay, so here's your formula. The measure 35 is inserted along with your population mean and the standard deviation. 35 minus 15 is negative 15, divided 35 minus 50, is negative 15, divided by 10 is negative 1.5. So your z-score there is negative 1.5. Z-scores are usually fairly small. The mean of a population is 40 with a standard deviation of 8. Find the value that has a z-score of 2.2. Okay, so here the isolated variable is z, but we actually know the z-score. So when we insert this, it's x, the measure we're looking for here. So we have to do a little bit of algebra. Okay, there's the same, that's where we were. So we're going to multiply both sides by 8. 8 times 2.2 is 17.6. Then add 40 to both sides. So in this situation, a measure of 57.6 would have a z-score of 2.2 if the population mean was 40 and the population standard deviation was 8. Some observations here. If the z-score is positive, the measure is larger than the mean. If the z-score is negative, the measure is smaller than the mean. The larger the z-score, the farther the number is from the mean. Okay, therefore, the more extreme that number is. Okay. Again, when you look at z-scores tables, which we'll get to later, z-scores are typically not very far away from 0. Okay, so to say 2 or 3 would be a large z-score. Here's a third example. You know that a measure has a z-score of 0.2. What do you know about this measure? Okay, well, 0.2 is a relatively small number, very close to 0. So we know that the measure is slightly larger than the average measure. Okay, so you're on the large side, but not by much, according to the small z-score. A measure of relative standing is a way to describe the relationship between a specific value in a data set with the rest of the values in the set. So z-score is a measure of relative standing. It lets you know how, like that last example, how does a particular value measure up? If your z-score is 0.2, you know you're slightly larger than the others, than the average of the others. You're on the slightly larger side. Okay, you're not larger than all of them, but you are on the slightly to the large side. To standardize is to cause a value to conform to a standard. So in this case, our standard is kind of the mean. We're comparing everything to that standard or the mean of the data set. Our standard says to calculate and interpret z-scores as a measure of relative standing and a method of standardizing units. So we saw the formula for z-scores, we interpreted what z-scores mean, and we use z-scores to compare a particular value to the other values in the set and to standardize it towards the mean of that data set.